Welcome to Fun Facts Daily, your source for just the good stuff. Monday through Friday, we're bringing fun facts and news you can use, all carefully curated to uplift and inform. So give yourself a break, relax, and learn something awesome in just a few minutes every day. Hi everyone, I'm Kyle Wood. Today we're going to be learning all about magnets. But before we get into the facts, let's warm up our brains with a little challenge to see if you can tell fact from fiction. Consider this. We all know that magnets will cling to metal, but will all magnets cling to all metals? What do you think? Are all metals magnetic? We'll find out at the end of the episode. Now for your word of the day. Our word for today is ferromagnetic. Ferromagnetic. Ferromagnetic is a term describing materials that are strongly attracted to magnets and can even become magnetized themselves. The ferro part of the word comes from the Latin word ferrum, which means iron. Which makes sense because iron is a classic example of a ferromagnetic material. The concept of ferromagnetism is deeply tied to the atomic structure of certain materials. Within these materials, there are tiny regions called magnetic domains, where the magnetic fields of individual atoms are aligned. When an external magnetic field is applied, these domains can align with the field, causing the material to become strongly magnetized. This unique property is what makes materials like iron, nickel, and cobalt so responsive to magnets. Time for your daily high five, our top 5 fun facts about magnets. Number 1. The Earth itself acts like a giant magnet, generating a powerful magnetic field that protects our planet from harmful solar radiation. This massive magnetic field, known as the magnetosphere, extends far out into space, acting as a shield. It deflects charged particles from the sun, preventing them from reaching the Earth's surface and stripping away our atmosphere. Without this natural magnetic protection, life as we know it would be very different, and our planet would be constantly bombarded by dangerous cosmic rays. The Earth's magnetic field is generated by the movement of molten iron in its outer core. As this liquid metal churns and flows, it creates electric currents, which in turn produce the magnetic field. This dynamic process is incredibly complex, and it's still an active area of scientific research, but its existence is absolutely vital for life on Earth. Number 2. Magnets were first discovered in ancient Greece thanks to naturally occurring magnetic rocks called lodestones, and the very word magnet comes from that ancient Greek region where those stones were found. The discovery of magnetism dates back thousands of years. The story goes that shepherds in Magnesia, a region in ancient Greece, noticed that their iron-tipped staffs were attracted to certain black stones found on the ground. These mysterious stones, which could also attract small pieces of iron, were later named lodestones or leading stones because of their ability to point towards the north. And this ancient Greek region of Magnesia is where we get the word magnet itself. This initial discovery of lodestones sparked curiosity and wonder, leading to early experiments with their unique properties. While the scientific understanding of magnetism was still centuries away, these naturally magnetic rocks laid the foundation for future innovations and our eventual mastery of magnetic technology. Number 3. Many animals, from birds to sea turtles, possess a remarkable sort of sixth sense that allows them to detect and use Earth's magnetic field for navigation. This incredible ability, known as magnetoreception, is like having an internal GPS that helps these creatures find their way across vast distances during migration. Scientists are still studying the exact mechanisms, but it's believed that some animals may have tiny magnetic particles in their bodies or specific proteins in their eyes that react to the Earth's magnetic field, allowing them to literally see or feel the magnetic lines of force. For migratory birds, for example, magnetoreception is crucial for their long journeys, helping them stay on course even on cloudy days when visual cues like the sun or stars aren't available. Sea turtles use it to navigate back to their birth beaches, and even some insects like honeybees use the Earth's magnetic field to orient themselves and build their hives. Number 4. The strongest magnets in the world are made from rare earth elements, particularly neodymium and samarium. Neodymium magnets, often referred to as neomagnets, are made from an alloy of neodymium, iron, and boron. They're incredibly powerful and used in a wide variety of modern technologies, including headphones and in-ear monitors enabling high-fidelity sound with small drivers. Similarly, the vibration function in smartphones and haptic feedback devices often relies on tiny neodymium magnets. But it doesn't stop with those smaller devices. Neodymium magnets are pivotal in the auto industry as well, particularly with electric vehicles and hybrid electric vehicles. Their high magnetic flux density is essential for the efficient electric motors and generators, contributing to better fuel economy and extended range. They're also found in power steering systems and anti-lock brakes. Neodymium magnets pop up in wind turbines, medical applications like MRI machines. It seems like neodymium magnets are just about everywhere. Samarium cobalt magnets are another type of powerful rare earth magnet, though generally not as strong as neodymium magnets at room temperature. But samarium cobalt magnets excel in high temperature applications where neodymium magnets might lose some of their strength. And our fifth and final fun fact for today: magnetic levitation, or maglev, is a real technology used in some high-speed trains, allowing them to float above the tracks and achieve incredible speeds. Maglev technology uses powerful electromagnets to create both lift and propulsion, eliminating friction between the train and the tracks. The train cars are equipped with magnets that repel the magnets in the guideway, causing the train to hover a small distance above the surface. This works because magnets have two poles, a north and a south. Just like two north poles will push each other away or two south poles will push each other away, the maglev train uses this repelling force to lift off the track. By using the like poles to create a repellent force that makes the train levitate, they've eliminated just about all of the friction that would have come from the physical contact of a traditional train with the tracks. This allows for extremely high speeds with less energy consumption and a smoother ride. The development of maglev trains has been a significant engineering feat, with operational systems in countries like Japan and China demonstrating their potential. While still a specialized form of transport due to infrastructure costs, maglev represents a fascinating application of magnetic principles and holds promise for future advancements in high-speed travel. Now for some news you can use. We've all been there. You drop a screw, a pin, or your keys into a hard-to-reach crack or under a heavy piece of furniture. This is exactly the kind of scenario where magnets can come to the rescue. Attach a strong magnet to the end of a stick, a string, or even a flexible ruler. This kind of improvised magnetic retrieval tool allows you to reach into tight spaces and pull out lost metal objects without having to move heavy furniture or contort yourself into awkward positions. The magnet's force will grab onto the metal item, letting you safely lift it out. It's a clever way to turn a frustrating situation into a quick and easy fix thanks to the science of magnetic attraction. Now, on a related note, if you've ever tried working with tiny screws, you know how easily they can slip off a screwdriver. That's why having a magnetic screwdriver can be incredibly helpful. The magnetized tip will hold the screw securely, preventing drops and making it much easier to guide the screw into place, especially in awkward angles or tight spots. Many dedicated screwdrivers come with this feature, saving you a lot of hassle. But if your tools aren't already magnetized, you can actually do it yourself. All you have to do is take a strong magnet and rub it along your screwdriver or whatever other tool you might want to magnetize. Do this about 10 to 20 times, but make sure you're always moving it in the same direction. This process aligns the tiny magnetic particles within the screwdriver's metal, giving its tip a temporary magnetic charge. It's a quick and free way to add a helpful magnetic boost to your tools when you need it. Now for the moment you've been waiting for. At the beginning of the episode, I asked, are all metals attracted to magnets? Well, that's false. Not all metals are attracted to magnets. It's a common misconception, but the truth is that only certain types of metals, specifically ferromagnetic materials like iron, nickel, and cobalt, are strongly attracted to magnets. Other metals like copper, aluminum, and gold don't exhibit significant magnetic properties. And now I think it's really important to explain just how magnets work. At its core, all magnetism comes from moving electric charges. It's from the movement of electrons within the atom. Every atom has electrons orbiting its nucleus, and these electrons have a property called spin. Both their movement and their spin create a tiny magnetic field, making each electron like a microscopic magnet. In most cases, these tiny electron magnets are pointed in random directions, or they pair up with other electrons spinning in opposite directions, which cancels out their magnetic fields. So even though every electron is essentially a tiny magnet, the material as a whole doesn't act like one. But in special materials, particularly ferromagnetic metals, something unique happens. They have unpaired electrons, and their atomic structure allows the magnetic fields in these electrons to naturally align with each other within small regions called magnetic domains. In an unmagnetized piece of iron, these domains still exist, but they point in all different directions, canceling each other out. When you expose this material to a strong external magnetic field, like another magnet, these tiny domains can snap into alignment, like tiny compasses all pointing the same way. When enough of these domains are aligned, the entire material becomes a strong magnet. Other metals, like aluminum or copper, are either paramagnetic or diamagnetic. Paramagnetic materials have some unpaired electrons, so they're very, very weakly attracted to a magnetic field, but they don't hold on to that magnetism once the field is removed. Diamagnetic materials, on the other hand, have all their electrons paired up, so they actually create a very weak magnetic field that opposes an external magnet, causing a slight repulsion. But these effects are usually so tiny you wouldn't notice them in everyday life, unlike the powerful pull of ferromagnetic materials. So it all comes down to the electrons and how their tiny magnetic fields are organized within the material. And while magnets can certainly have a powerful pull, their attraction is just to a select group of metallic elements. Now, I hope you enjoyed learning a bit about magnets with me today. Be sure to tune in every weekday for even more fun facts. Fun Facts Daily is an Airwave Media podcast. It was written, recorded, mixed, and edited by me, Kyle Wood. Thanks for sharing a part of your day with me. Be sure to follow Fun Facts Daily on your favorite podcast app so you can keep the good stuff coming your way every day. And if you like the show, please do me a favor and leave a kind rating, review, or just tell your friends about it.